Supposed to turn this off and on every once in a while, so otherwise it's a big old file that's 2.5 hours long and they can't download it. All right. Somebody had a question. Mark, you have a question?
No.
Oh, okay. I thought I heard somebody have a question. Okay, good. We'll just designate R1, R2, and R3. And if I tell you that it's 100 ohms, 200 ohms, and 300 ohms, you know right away, Casey, you know that you just add those up with standard RT equals R1 plus R2 plus R3, right? So you just do it. Now, if it was on a test, I'd want to see it done. I know you can just do it in your head, write the answer down. But if for some reason your brain just goes off in la la land and you make a mistake, then the answer's wrong and I can't see your mistake. And if I know that you knew how to do it and you just fat fingered the calculator, you know, I do that sometimes, and it came out with the wrong answer and you wrote it down, I just mark off for the answer. But if you don't have any work there, I have no idea if you knew or not. So, okay, so that's how it works. All right, do we have to be mindful of the tolerances? Well, no, because it's an ideal circuit. But when we put the circuit together, we will have to be. So how would we know the resistances of the resistor in the real world? I told you to put this circuit together and you had those 3 resistors and a 9-volt battery. How would you know if those resistors were those resistances?
Markings, bands.
Bands?
Use your ohm meter.
Your ohm
Right
meter.
on there.
Ohm meter. Because the bands still tell you the ideal, right? They give you a tolerance, don't they? But you still don't know if the resistor's high or low, right? Or perfect. So you have to use an ohm meter. So let's think about how an ohm meter works. You guys ever use an ohm meter? Anybody? Okay. It has scale on it, just like you look at your meter. It has scale. See the little ohm? Turn it to that. Turn it to the smallest one, 200. So what does that mean? That means that you're going to measure a resistor that is less than 200 ohms. Okay? Just like the voltage. Okay? Just like the current. 2K, what's K stand for? 1,000. M? Megohm. Million megohm. Okay? All right, so we're at 200. Can we measure all of those resistors up there?
No.
One of them we can't, right? We're going to have to go to 2K to get that one, right? Okay. I suggested you start with the other 2 and do them and then move to 2K and do the 300. I would not do all of them under 2K.
Why is that?
Because none of that accurate. It moves the decimal point, so you lose one, it drops off. It may not be a big deal in this particular case, but in some cases it is a big deal to know what that last digit was. Okay? So try to get it under the umbrella with the lowest possible size. Same with voltage and current. That way your accuracy is better. Okay? So you kind of have to move your meter. That's why you have to know how to use your meter. Okay? All right. By the way, just to drop back to your current, just real quick, if you look at your scale on your current, it's like it goes from, I think these do 10 amp, and then it goes 1 amp, I think, and then it drops into milliamps. That's millionths of an amp, okay? And it goes down, what's the first milliamp it has, do you know? Let's see here. Okay, so it has 200, 20, and 2. Okay, so 2 is smallest, 200, then 20 amp. Boy, this thing will do.
Volts, aren't you?
Oh, where are we at here? No, where's your, let me turn this around. Okay, so you're looking at, oh, let's see, where is your current here for, that's farads. Let's see. Yeah. This is the first time I've actually looked at these meters. There's your voltage, there's your current, and then there's your amps for AC. Where's your DC? That's gotta be, yeah, okay, your DC amps to the right says 2 milliamps, 20 milliamps, 200 milliamps, and 20 amps. The 20 amps, you have to move the terminal to 20 amps. Now, if your terminal's in 20 amps, you need to move it over to, you need to put your black one in common, and then you need to put your red one under volts, ohms, hertz. Okay? You guys got it?
Red under volt ohm hertz?
Yes. Now, your meter will measure 2 milliamps to 200 milliamps. The 20 amp, you have to move it over. You notice how it has a terminal on the other side? Most of them are 10. These are 20. That's really good. Okay? So when you do that 20 amp, you have to move it over so it goes through a shunt in there and it doesn't burn your meter up. So everything there is in milliamps, and we'll do DC. We'll work in DC. There might be an occasion where we use the AC side, but not very often. It's all DC for us, pretty much. Okay?
Well, the DC is just one squiggly line under it?
It's the DC is the. It looks like this.
Dotted line?
Okay, yeah. You got an A, and then you got dotted lines, and then you have a steady line. Okay? You see that? Okay, it's on your meter to the left there. The other one has the squiggly line. That's AC. Yep, see that little guy there? Oh, I got the line wrong, don't I? Sorry about that. Okay, so it's going to be solid line, dotted line. Okay, and that just means on, off, but DC solid. Okay?
How much do these ones cost?
Don't know. They're fairly expensive because they're better than there's a little green one there behind you.
Yeah, but that one actually has a brand name from America. You could have bought that one.
Yeah, those are way cheaper. And you can buy meters online really cheap, you know. Just look around. You can get used ones on eBay, really, really reasonable. I bought a lot of them off of eBay, and I've never really had too much trouble with them. So I hate to tell you this, but China's got really reasonable ones. I don't like buying from China, but they have such good prices. You know, you just... Yeah. All the money's going to be worthless anyway, so it won't matter. They'll have all that paper and it won't be anything
We'll
in
work for China if Hillary gets it.
Yeah, we sure will. Let me turn the camera off here and then we'll talk about that. All right, we're not supposed to talk about political things, but let me tell you, I'm thinking either one of them get in, but I know one thing, when Hillary gets in, we're really dead. We're all dead.
Literally.
Literally, yeah. Okay, so that's the current scale. All right, so we're looking at these resistors, and so Casey, is this the correct equation? RT equals R1 plus R2 plus R3. And if I add them all up, I can just say RT equals, I'm just going to denote it here. I'm not going to put it in. You should.
Yeah.
Okay? And if I add them up in my head, it's what, 600 ohms? And I know that 600 ohms is ideal. There's a combination of tolerances that will either make the total higher or lower, right? Or right on, right? But one way or another, the first one might be a little high, second one a little low, next one a little high. So if I make the measurements on there, when I get to the end, all my measurements are going to be different than my neighbors. And my total is going to be different than my neighbors. My battery is going to be different than my neighbors. But it's going to be within a certain tolerance so I know that it's right. Because I'll calculate the tolerance 5% for each of those with a gold band. Because I'll tell you that. I'll say they're all gold. That's what we're going to engineer with, is gold bands, okay? So they're all gold bands, and immediately you will show all of that calculations on your sheet. That's what engineers do, okay? Now, if you're just the engineer, you'll just do all the ideal stuff, show all the tolerances, show all the different circuits that could occur, and you'll hand it off to somebody to build, and they'll see if it's going to work or not. So they'll take the resistors and plug them in and see, okay? If you're the type of engineer that does the actual triple ET, that actually does the work, you'll calculate it all out, and then you'll do it. You'll actually build it. That's probably what you would end up being, because most small companies can't afford to hire both. So you get to be both. And actually, to me, that's the most exciting part. Just doing it on paper all day long would really bore me. And just sitting on the bench and taking somebody else's design would upset me, because I'd want to do it my way. So I like being able to design it and build it. And I pick up special projects that I do that. But that's another story. All right, so let's just assume it's ideally 600 ohms. Immediately, I know something about this circuit. I now know that I have 9 volt, plus and minus, and an equivalent circuit of 600 ohms called RT. I want to see that equivalent circuit on your sheets. So in your notes, show it to me and show me the equivalent circuit. Okay? So Mark, now we can determine something else about this circuit.
Your amperage is 0.015.
We can determine the amperage. Okay? I equals E over R. Now, you may have to say here IT, RT, ET. This one doesn't phone home. Oh, that's a terrible joke. Shouldn't have said that. ET does not phone home here. ET is the total voltage. Now, why would you do that? In this circuit, doesn't make a lot of sense. No. But you may have a really complex circuit where you need to have different designators, T1, T2, and so on, before you solve the whole circuit, okay? So you want to make sure that you go put those identifiers on so you can tell where you're at, okay? And what did you say this current was going to be?
0.015.
0.015. Always place a 0 in front of the decimal, okay? So we can tell that there's a decimal there. Otherwise, it kind of looks like maybe there was a mosquito and he landed there and you swatted him, and now you got a decimal point where you didn't want it, okay? Well, you get the idea anyway, okay? And, okay, the identifier for it would be amps. You gotta put that on. It's not ohms, it's not volts, it's amps, okay? All right, so now that we've got that, then we can back up. We can say, okay, we have a law about current. What is it in a series circuit? Casey, did you learn that law? Mark. No, Mark, Joss.
Sean, Steve.
Sean, Steve. You see how terrible it is? I am so bad. I'm just like, hey, you. You know.
No, yeah, my favorite name.
You know, I've been a fireman for 31 years, and I've seen firemen come and go in our fire department, and I can never get the names of the new guys. And you know, when you're out on a fire scene, it's just not a good thing to go, hey, you over there. That's not a good thing, you know. They're like, who are you? Well, they know who you are, but they're like ignoring you, you know. So, anyway. All right. There's a rule about current in a series circuit. The rule is, pencils, paper. The rule is that the current in a series circuit is the same in all of the components. You've heard that rule before, haven't you?
Yep.
Yeah, so write it down. So that makes this circuit easy, doesn't it? Mark, what do we know about the current? You had the current, you calculated, you gave it to me. I know that this current is, and I'm going to show it. Which direction do I put the arrow for current?
Negative, positive.
That direction. I will denote it with I. And I know that that current, because it's a series circuit, is the same in all the components. And I know what that current is. What did we say it was, Mark? 0.015 amps. What does that give us now?
Gives us power.
It gives us power, but it gives us something else for each of the components. What can we now calculate?
Voltage drop.
Voltage drop across each of the components, and that should add up to 9 volts, shouldn't it? Right? So now, what is the equation for volts? E equals I times R. Okay? I can plug in each one of these because I now have a current and I have a resistance. Right? I'll do the first one. So I'm looking at it and I'm going, okay, I got 100 ohms and I got 0.015 amps. E of R1 equals I R1 times R1. E R1 equals 100 times 0.015. Now, here's where you just shuffle the decimal point. How many places do I shuffle the decimal point if I multiply by 100? 2. So my voltage is 1.5 volts. Agreed? And you can do the rest of them, right? All the way across. And it better add up to 9 volts or you got a problem, ideally. Okay? Now, if you're doing it practically, you measure your voltage of your battery. If it's 9.3 volts, they better add up to 9.3 volts because you can't make or get rid of voltage. It has to add up to that voltage. Dean, sit down.
It'll never be the same.
As the battery voltage?
No, just because your resistors, like you said.
Yeah, they're going to all be different, but when you add them up, they got to add up to supply voltage.
On paper.
And in real life, if you have more voltage in your resistors than you have in the battery, you got a problem.
So let's say that 100 ohm was 99 ohm.
Right.
Because it's in the tolerance.
Right.
And you take account for that.
Okay, when you measure this across here, instead of 1.5 volts, maybe it's 1.43 volts. And this one's different, and this one's different. But when you add those up and you measure across your battery, those better equal what's on the battery. I mean, obviously they might go out to you could go out to 9 places or something, but it better you better not have 8.2 volts on your battery and all your resistors add up to 9.3 volts. Unless you got a joule thief. You ever seen those joule thieves where they go, well, you can get power out of the air. Well, why do you have to use a battery if you can just suck the power out of the air? You know, I've always wondered that because all of them use a battery, you know. So you cannot create electricity out of thin air. So practically, they're going to be all different, but the source has to equal whatever the passive or active devices are, whatever they show as a drop, okay? And we're going to do that. In fact, we're going to do it right now. I want to talk about your breadboard real quick for a minute here. You guys used breadboards before, right?
Yep.
Okay. The only thing that I require when you use your breadboard is I require that you use the rails, they're going to be blue and red on each side. I require that you hook plus here and minus here. Do not put them right close together, okay? One side or the other. I don't care which side, but they need to be opposite each other on both sides. Why is that? It's because when you get to digital, you're going to plug a chip in there, and it's easier to jumper the power. You don't have to use long leads. They're made to do that, okay? And when you build your circuits, again, you're going to want to be able to come in from each side. If you have the rails right next to each other, then you have to jumper everything over the top of the chip or the transistor. And it makes it a real mess when you try to pull something out and put something in, okay? So that's the only requirement that I want with your breadboards. You'll need to remember that when you build a circuit, the area on the breadboard is limited. The first circuits you build, you can just put them anywhere, but the more complex they become, the more you need to pay attention to your board and where you're putting your circuits and how you're wiring them up. Or they will become so complex that you will not be able to figure them out. You'll have jumper wires all over the place and here and there. I've seen people with multiple grounds and they can't figure out why they got multiple grounds and all that kind of stuff, so real messes, okay?
Can you give us the flat jumpers too, or no?
We're actually going to make our own. We'll use these now, but we'll make our own out of just wire. We'll just strip some wire. Because you guys, I don't know if you've got these at home and they're fairly cheap. Let's say you get somewhere and you just don't have jumpers. You can just take some old Cat 3 telephone wire, strip it off, solid core, clip it, strip off the ends, you got jumpers. Okay. Braided does not work in a breadboard. I mean, you can get it in, but it's really hard. So you want to look for solid core, okay? If you're around and somebody has a roll of that old Cat 3, they'll give it to you for free. Grab it, put it under your bench, and then you can clip off a piece. I got a big old roll somewhere. I hope it came down. And I just been clipping it off and making my jumpers, although we did get these nice new ones. So they're nice. We'll use them today. Okay? All right. So all of your circuit will go in here. Just remember that you have to look after the amount of space you have on your breadboard, because sooner or later you're going to run out of space. And then you're going to be in trouble. Okay? If you like to save your circuit, that's fine. There's going to come a point where you're going to have to take the old circuits off and put new ones on because it'll get so complex. Okay? All right, so for your lab, and now we need a new page in your notebook because it's going to be lab 1. We'll call it 1A. How's that sound? Yes, sir.
Take a break. Bathroom break?
Oh, yes. Yeah. If you need to go, go. Let's just take a couple minutes here, okay? I know it's a long time. We got another hour to go, so you guys need to take off for a minute. I'm going to stop this recording.